Yes, sir.
Okay, so we are in lecture number 5, and this is AI generated or assisted chip and digital design course, primarily learning how to uh, use generative AI for algorithm to silicon mapping. Obviously, two parts of the course. One is understanding what type of algorithms uh, are good candidate for silicon mapping. And then the other part is how do you go about doing this. Um, so today I intend to do review of lecture 4, which perhaps I'll first take an example uh, to demonstrate uh, another algorithm which is being used a lot, and going to the intricacies of the algorithm, and then just seeing that the approach that we are learning in this course, divide and conquer, how easily we can generate architecture or generate Verilog code uh, for pretty complex algorithm. So, and then I'll go and review the HDL that we have been studying, and this is the slide which we will keep seeing in the course. Uh, that still we are at the RTL level, that you have defined an architecture and then coding it in RTL. And today we will briefly touch, if we have time, about the functional verification, and then subsequently we'll go and see what is meant by synthesis. And so, but because tools are getting stronger and stronger, and that is kind of giving me leverage to focus more, and this is what we need to learn: focus more on the architecture. And tools will be very good, so especially just uh, taking Verilog code and generating a netlist, doing a placement and routing, especially of the digital design, would be would a lot be depending upon the tools, and very little perhaps what you can add value into what tool is doing. So we have learned about, and that is what is called abstraction, that you are keep increasing the level of abstraction, where you take a real life problem, and because of, not because of love of architecture, but because of genuine reasons, that you go and you say that you're going to do this in hardware, and do the architectural design and then coding, verification, and synthesis. And we have seen again this colorful depiction of the course many times. And so this is assignment number 2, which was due on the Sunday. I hope that most of most of you could able to do this assignment. Let me grab this water bottle. Okay, so but we'll keep discussing problems like these. And here again I'll be keep emphasizing about the impact on the design of your early design decisions, where you have conceptual level, and then high level, and then the RTL level view of the problem. And the rest is, as I mentioned earlier, because you're going towards high level of abstraction. First, a change here would be very complex to make. If you're trying to fix the architecture, once it is all done, it'll be very complex to make changes. You could only make changes just fixing bugs, and very little few changes which you could able to make, but not major design. You would not able to change once you are at this level, or even at the RTL level. So most of the thought in the design should have gone before you committed to generating a register transfer level code, or the design of your of the application that you're building. So today I have something very interesting algorithm. So first I'll discuss this algorithm, and then how this works, and why it is such an important algorithm that is a very good candidate of its implementation in hardware, it is hash 256. And if you want to see how the hash works, you can click on this link and it'll show you a nice explanation and animation of the algorithm. So it is used in whenever we say digital transformation, like digital Pakistan and digital Malaysia or Bangladesh or India, or any such thing. It primarily, though you are digitizing the processes, but it's a lot more than that. It is about you signing something digitally, and it should be acceptable by the state. So signing digitally does not mean that you take a pen and you sign. It means an actual digital signature, which is generated by your wallet, and your wallet has a private key, and that private key primarily is used to sign your document, sign degrees of a university. And so digital transformation is kind of based on acceptance of digital signature by state-owned entities, and not only that, but the other businesses that they value that, okay, this is a transaction is being made through a valid, and transaction does not mean just a transaction in rupees. It's a transaction where you are getting your transcripts, a transaction where you're getting your degrees, your health record, or anything that has value, where they ask you to come, please kindly sign here. And so that is a transaction. And same is like Bitcoin transaction. Um, so in even Bitcoin transaction, usually you are sending some Bitcoin from your UTXO, so to say, to somebody else's UTXOs. So here the payment is being sent to this account with this ID. And because you got to, in Bitcoin, we say you got to consume a complete UTXO. So in that consumption, there's always some money left, which you send it to yourself. So usually a Bitcoin transaction has two parts. One part that goes to a person or a wallet, and then second part usually comes back to you, your own wallet. So hash is, as I mentioned, is so fundamental to digital transformation, and for many reasons. And some of the reasons are here. Then it is, you cannot reverse it. Knowing the hash, you cannot go back and generate the actual message. So usually n bit input, no matter it is 1 bit or like 1 gigabit of information, everything gets compressed into 256-bit word. And because you are just compressing kind of all the information, so it's not possible. So nobody cares about, it's not like encryption where you got to decrypt. So it's very difficult for anyone to take the hash and find out. Even just finding out how big the message was is not a tractable problem. So what to talk about exactly figuring out the message. So that's why it's kind of give an identity to a content. Okay, so your book has a hash, means anybody changes even a space in it, the hash will change, and a little change will make a big change. It's called avalanche effect. So avalanche effect is almost every bit of the, or at least every byte of the hash will change its value. So you will see very little change that you are making to the content, everything will change. So it's called the avalanche effect. And determinism is that no matter how many times you take the hash of the document, it will always come out to be the same, and nobody can predict it. And it is Clean resistance, mean no two documents will have the same hash, and it is 2 raised to the power 256, whatever. So these are the number of possibilities. So that's why a hash is used a lot. And an interesting problem is the miners, that how the miners mining is nothing but computing hashes, and and millions and billions and trillions of hashes that you have to compute to get the reward. And we know there are many people who are interested in making money being a miner. So that's also one of the it's just one of the many applications is that you want to be a miner. Miner is that you are mining the bitcoins, and as I mentioned, mining is nothing but taking hash. And how it happens is that every transaction, as I mentioned, that you just put it in this hashing algorithm and get a 256 bits and 256 bits. So every transaction you take a hash, then you combine two hashes, create another hash, and similarly you keep making a tree, taking hash, 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 and finally you have a this is called the Merkle root hash. This is the hash of all the transaction in a block. So in a Bitcoin block is that every 10 minutes you collect all the transactions where people are sending money from one user to another. Uh, and so every 10 minutes you create a block. And that's why it is called blockchain. And all the miners, they are just trying to be the winner, creating a block. And anybody who is a winner would get 6.25 bitcoins as a reward, and it started with 50 bitcoin, and every 4 year it gets halved. So I think in 2024 sometimes I think either it has already been halved or it is very close to getting halved again. So hashes, and then what you do is, so you have all the transactions hash, Merkle tree hash, then the previous header hash, which is a hash which was the block which was previously mined, and that's how you make it a blockchain, because you have this hash. Anybody changing anything in the previous block, the hash will change. If hash will change, anybody who's proving if this hash changes, then the next hash change. So you can easily go back and see that who has made any change, because that's how they are just connected through hashes. And because you have the hash of the previous block in creating the hash of the current block. So this is the Merkle tree hash. This is the magic number that all miners are trying to do. So it's annoyance is just a random number that you keep putting in, because it is not deterministic. So all these three together, and the timestamp, uh, and you got to create a hash so that you get some leading number of zeros. And because it's not deterministic, you try. It's very hard to even get first zero at this location, because you don't know which number would cause. This is fixed, this is kind of fixed, this is changing, and this is kind of the only variable. It's a random number that you put a random number, create a hash, see if you have get like 24, 25 leading zeros. Anybody who gets all these leading zeros is the winner. And 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 you don't know. Only thing you can do is just create billions and trillions of hashes with all possible random numbers to see that if you could get to the all zeros to get the reward. Okay, so this is how the algorithm works. You have the previously mined block, which has all the so a transaction would take several blocks to be confirmed that your transaction has become part of the blockchain. So that's why there are exchanges which instantly just do the exchange, but they are doing it on their own ledger. So the blockchain only works after 10 minutes a block, and then it takes like a couple of blocks. So only then you will be um, confident that your transaction has been part of, because many miners are trying to win the rewards. So sometimes they may go in parallel. So only there will be only one. It's a distributed algorithm. Only one path will go forward. So you take a previous block hash, and then you have the current block, and you select the number of transactions, create a Merkle hash, and then you have this random number which is called noise, and you create a hash, and this hash should have all these leading number of zeros. If it does not, and then you got to do it again and again and again and again and again and again, and then so doing it trillions of times. And this is has to do with some mining difficulty. If it finds people have enough computer, they're doing it shorter than 10 minutes, the algorithm by itself will increase the difficulty level, so that still it'll take on average everybody to spend 10 minutes, no matter how much compute you are putting in, 10 minutes on the average to mine a block. But a lot of hashing, and anybody who gets this all these zeros is the winner. So here is an example. This is the block number 776151, and somebody is the winner because he could able to get all these zeros. And how could he get all these zeros? By putting a noise, and these are the number of transactions, in the block. This is how a specific transaction would look like. And here is so all the zeros. So anybody who gets all the leading zeros in the block hash is the lucky winner. And he has already put a transaction into the blockchain, which says 6.25 Bitcoin goes to him, to his wallet. And this is how the we could say this is a controlled inflation, that every 10 minutes only a fixed number of Bitcoin are produced. So it's not like any government just inflating the economy by printing as much money as they want to. So it is, that's what. So this is the noise. Here is the random number for this block. Okay, so it's a random number. This is the reward money, and so important is a lot of hashes, hashes are happening. And so these are the block. And blockchain, as we know, uh, hit actually $64,000 a Bitcoin, and the mining, and then you can multiply it with 6.25 to see that how much money you make. I don't think so it is legal, so I'm not motivating you to be a miner in Pakistan, but I'm just telling you that this is nothing. Mining is nothing, but just doing all these hashes, because hash is so specific an algorithm. If you do it in silicon, you get a lot of speed up, and you can just make it go as fast as the amount of silicon you have. So that's why uh, becoming a miner is not that difficult. And so people have come up with ASICs. So there are a few companies who are building ASICs uh, for you to be a miner, uh, and they compute a lot of hashes per second. And this is the price of a single chip, but you can definitely do it on an FPGA. So that's why this hash is important. And as I earlier mentioned, it's not about the Bitcoin. It is about the digital transformation, so to say. So anything we want to do digitally, and because once every transaction that we're processing, you got to check whether the digital signature is a valid signature. You have to compute the hash. So hash acceleration is core to digital transformation. Uh, and we will be covering that, how you do digital signature in a while. But what it does is that if you have a message, a document, your degree, your transcript, so everything in that uh, gets converted into uh, an ASCII code. Okay, if you have your name, or let's say you have this message ABC. So A, we know the ASCII is this 8-bit number, and then 98 and 97. So you have a message, and the message is gets converted into binary number. So even space, you can compute a hash of a space, because space also has an ASCII character. Your name has an ASCII character. So the assignment we are going to do would have your just name, and we are going to create a hash of your full name, or maybe first part of your name. So you have you convert it into ASCII character by looking into this table. So you go find out if my name is Shoaib, so I'll go find out ASCII of S, then H, then O, then A, and then B. So if you have this, but in this case, your block size has to be 512 bits. So you need to pad this with a lot of zeros to make the massive size 512. What if you have a book? So if you have a book uh, full of words, so you make 512 blocks of 512 bits, and the last block will not have 512 bits. So you need to deal with the last block like this. Like if it is not 512 bits, you write this, and then you append a 1. So you append a 1 in the last. So this is what you do. Okay, and then so this is kind of end of the message, and you won. And then you fill it with 512 minus 64 bits. So you leave 64 bits to put the length of the message. So here is all the zeros. So you have 512, but you got to leave 64 bits at the end. Why? This is the length of the message, that into 2 raised to the power 64. So you can imagine how big a message you can have to create a hash of that message. So you fill, this is an extra one that you have added, and these are all the zeros, and you are here, and here is what you put, the size of the message. In this case, these are 24 bits. So you put 24 is 11000. This is 24, and so this becomes, yeah, I think you need to turn off your mics, please. You, so you need to turn off the mics, please. Uh, I would request everyone to turn off the mics, or I would request Laiba to turn off all the mics, but don't turn off mine. And then if anybody has any question, you can raise your hand and she will turn your mic on. So this is how you create a block. The fun starts from here onward, and then that you have a message, 512 bits, and 512 bits you divide them into 32 bits each, mean into 16 parts. So 512 bits, 16 bits, 16 bits, 16 bits, 16 bits, and how many of these? 32 bits, 32 bits, 32 bits, and 16 of this. So 32 bits is the your size of 1 unit of message, which is called M1, M2, and MN. So so these are 16, but you're not going to expand it to make it 64. Like out of 16 32-bit words of a message, you have a scheduler which is going to expand it to 64 bits. And so these are your, let's say, original message, which in this example was ABC. This is the one you added. These are all the zeros, leaving 64 bits in the end and putting here 24. This is our original message. 32-bit each means this is word 0 to word 15. So these are the 16 bits. So word 16 is the 16 bit. And then there is a way from the same message by a little manipulation. So it's not a lot of compute here. You can do this in software as well, and we'll get to where there's a lot of compute. So you have this message, and from just a combination of uh, uh, these 16 32-bit words, you are going to create another 48 words to make uh, them to 64. So this is how you basically take uh, the message at T, and then first 16 are as they are, and rest of them are created by just by making use of the one you are creating, going two position back. This is going 15 position back, and this is going 16 position back. So just adding the 16 position back message, the 7th position back message, and doing something which is a function with the message which is 15 position and which is at the 2nd position. And so what you do is you just rotate the message. For example, here is t minus 2. So t minus 2, you go back 2 steps and take the message, rotate to it towards the right 7 position. 7 bits will come back and will be moved in the front. Then you move them the same message 18 bits. 18 bits will go around and come back. And then you do 3 bits. So you are just like we make lassi. So you're kind of making lassi, just making it so random that nobody could actually able to figure out that how you have created the hash. So so that's something uh, seems like stupid things, but that's how the algorithm works. And the people who have been like spending time, they are making sure that it is clean, free, that no two messages would have the same hash. So that's why they are doing all these kind of things to a message. And similarly, sigma 1, which is used here, do some different type of rotation, the 17th and 19th and 10 rotation of this message t minus 2. So this is how, like, you have um, this is x, then how you rotate 7 positions. So 7 of these will come on this side, and then you have 18. So 18 of these will come here, and then you have 3, and so that's how you XOR them together to create this message. And similarly, the other one where you 17 bits will, 17 of these will move and will rotate and come back here. And 19 of these, 10 of these, then you XOR them together, you get this. And so you have this schedule. These are your original message, which is going from 0 to 15. And these are the additional that you have, like the message going 2 step back is this one. And message going so many steps back is this message going 19 back is this one. So 1, 2, and 3. And you use them at the the new word in the schedule. So you extend it to from 0 to 63. So now you have 64 32-bit words. And so, and then is the actual algorithm. The actual algorithm, this is what you can, which I have tried putting it in hardware myself. And it took me only 5 minutes to generate an architecture and kind of the code. It's not complete, but I myself got amazed that the power of these generative AI tools, that if you just understand the problem and you just sit down to create an architecture, at least you know the first step. Uh, uh, a good working architecture you can make so quick, and then you can also generate its stimulus and check whether it is working or not. So here is the is the algorithm which I tried mapping in hardware. So here are 8 16-bit words. Uh, that's why it is called hash 256. So these 8 into 32 is 256. So this is hash 256. So 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 you need to instantiate 8 32-bit registers. You need to name them A, B, C, D, E, F, G, and H. Okay, so 8 of them. Your A in the next iteration, your A in the next iteration will become B. Your B in the next iteration will become. Now you are trying to understand the algorithm so that you can create a silicon version of this. So one part is very simple, that A becomes B, B becomes C, C becomes D, D does not rightly becomes E, rather it gets XOR with something which you need to compute. But E becomes F and F becomes G and G become H. The main thing is with A, that A requires a lot of things to be computed. So these are the things that you need to do. Compute to compute an A. This is choice as a function which takes E, F, and G and generate a 32-bit word. This is a summation 0. It's kind of the same thing what we saw rotations and stuff. So it creates 32-bit words. Majority is another function which takes A, B, and C, 32-bit words, and created 32-bit words. And this is sigma 1, which is again only takes A and generate 32-bit words. So these are 1, 2, 3, and 4 32-bit words. Here is your message, remember? So this message is what you created. And how many of them you have created? You have created from 0 to 63. So there are 64 of the messages. These are constant, and these are also 32 64-bit constants. And so these are the constant. So the architecture which I generated has not catered this, which I've left it for you to generate. So I'll give you the code that I've generated, and then I'll ask you to add the logic in this function, in this function, in this function, in this function, and also input to the module the message and the key. So here is your kind of the module which has an input, uh, WT and KT coming into it, and then you start with this one. So what happens is that you have to reset these registers to start with, all these 8 registers with these values. Okay, so these are the values which goes first in these 8 32-bit register. And so these are fixed. We need not to worry about this, but how they have generated this 8 32-bit words, it's by taking square root. It is a fractional part of the square root of the first 8 prime numbers. Okay, So this is how they are generating, ensuring that they are random and they are not correlated to each other or whatever. But so we need not to worry about. We are not creating them. We are just saying once I say reset, all my 8 registers should be reset to these values. Okay, that's how I perceived it. That I have this reset. I say I press a reset, and reset means that I'm just starting the hashing, um, and then these values should go in these registers. And then every cycle, I put one message here and the constant, and then it does this iteration, and all these register gets updated, gets updated, gets updated, gets updated. How many times? This is going to be WT is we have 64 words, so it is going to run 64 times. So 1, 2, 3, 4, 5, 6, 7, 64 times, and after 64 times, you have completed one block. So you move this to these registers, which are H0 to H8. So you move them to H8 register, bring the next block, do this again, bring the next block, do this again, bring the next block, do this again. And every time you only it is first time that you're going to initialize your registers with these values. The rest of the time you have the same, whatever you have computed, you reuse that, reuse that, reuse that. So the entire book gets into the this architecture. And finally, once you're done with the book, after the last block gets entered into this, you get a hash, and that is a 256 bits hash, which uniquely identify all the text. It may be your transcript, it may be the book that you have written, it may be a check that you have signed digitally. So this is so fundamental that everything that you are signing digitally, uh, we don't want anybody to change that. It's like a check. Nobody, once you have signed it, nobody should change anything. So anybody changing anything, was all digital, all the transactions happen digital. Anything making any change, the hash will change, your signature will not match, and you can go and catch that person. If it's a blockchain, you can exactly figure out that at which chain, which block somebody has changed the data. So the blockchain becomes also so important for digital transformation. And this really is what the digital transformation is means. It does not really mean just changing something which is happening as is processes, converting them into digital processes where you have a nice user interface and you are. This is digital transformation where you are signing off digitally. Whatever work you are given, you do it, sign it digitally, send it to the next person. And if you want it to be mutable, you also put the transaction in a ledger, and that would show that anybody making any change to that would be caught right away, because every time a transaction happens, it is placed in the blockchain ledger. So this is interesting. I thought that so so these are the constants, the k, the 64 of these constants. And again, we don't care that how they created, but these are the cube roots of the first 64 prime numbers. But these are 64 constants. So this is how it all starts, that you have first initial values A, B, C, D, E, F, G, H gets these 32-bit numbers. And then these are the constants of k. The first time you are going to use the first value, first 32-bit numbers, then the second 32-bit, then the third 30-bit, then next. So to process a block, these are the values of k, these k. So these are 64 constant values, always remain the same. So means you can put it in a ROM. You don't even need to save them in a RAM. So you could just hard code them in your Verilog code. Create these 64 32-bit values, and if you want to put them in memory, that is also fine. So this is going to be in a memory where you have 512, so it will be a 32-bit wide memory. Every time once you start, your first value will get in here, and its first value will get in here. Okay, and then it goes, you get XOR comes here, and then you have all of this, and you are updating the code. So this is k, and these are those functions which we say choice are a choice function where you have this ANDing and ORing and simple logical functions that you can ask the generative AI that create a function or a module which takes three 32-bit numbers and then produce an output according to this relationship. So it'll create a module for you. As we know, we said divide and conquer. And how we are going to do divide and conquer is that I'm going to write a function for this, a function for this, a function for this, a function for this. And I'll make my also generate a stimulus so that I check. And once I'm happy, I only say use these function F1, F2, F3, F4 inside my modules, and also input the module should be WT and KT, and then I'm all set to go. So this is where these functions are doing. As I told you, sigma naught is also just rotating. So all you have to ask the chat GPT to write a function which takes a 32-bit number input and rotate it by twice and rotate it by 13 time, rotate right by 13 time and by rotate right by 22 times and XOR three of these values together to generate a 32-bit number. Okay. And similarly, you are going to generate this function F1. Today, we will also study once we say what is meant by rotating function and task. Okay. So this is what is something that we are going to develop an architecture for. SHA-256 is called choice and sigma 1, sigma naught, and a majority function. And this is how it kind of looked like. So this is how the algorithm works. It is because a block has 64 32-bit words. And so there is another loop which is outside, which is like you take all the blocks of your document, if it is a big book, and then every block of 64 32-bit number, you're going to process it like this. So in Verilog code also, you got to compute T1, which is this function plus this function plus this function plus this, and then you compute T2, and then we have already seen A going to B, B going to C, C going to D, E going to F, F going to G, G going to H, and only E is not directly taking D, but adding something. This is addition, not XOR. And similarly, A has the maximum things happening to it, and then you add these two, go to A, and then next time, and you do this 32 times to run it. Okay, so this is going to be your assignment, that you are going to take your first name, so your name, and it is this. So you are going to create an ASCII for your name. So this is my S and H and O and A and B. So this becomes my message, and then I am going to put an 1 here and many zeros here, and then finally counting, I have my message size 1, 2, 3, 4, like it is 32, and so I write 32 here, and rest is filled with zeros. So this is going to be my message. So we are going to design an architecture that implements SHA-256, generates this RTL Verilog code to run one iteration. So I'm not into, because uh, but then I don't say it'll become very complex, but because I just want you to have a feel of that you can generate an architecture for such a complex thing like a hash algorithm, which is so fundamental to digital transformation. So you're going to do, this is what I generated, and I got really amazed that it was so easy to generate on this code. And what I did was I said, generate RTL Verilog code, which we are calling SHA-256, and said, let's only focus for some registers. And I said, once there is, so I want this module to have 832-bit numbers coming into the module. Okay. And then I want, once I assert reset, I want all these constants to go in the registers, and which are A, B, C, D. So I have defined it 832-bit registers, which are also the output, because these are the hash values. So I asked it, first I was trying to just generate only the registers. I said 832-bit numbers gets in, and if I set reset, they should get initialized to the initial values. Otherwise, A goes to B, B goes to C. Here is just simple assignment, but you ask it to do the other type of assignment. At this point, I'm saying just otherwise, just latch these values. So here I'm not changing. And then I started changing and then generating a function and another function and another function. And I could so easily able to do this in using the generative AI. So that is where I want to start. That we are going to learn enough RTL level Verilog so that if there is, we should able to read the code, and if we see a problem and if it which is easy to fix, we should just go and fix it. And definitely we can ask the generative tool also to fix the problem. But sometimes problem is so simple that you can go and fix it. But the important is divide and rule, that how you divide your design at architectural level, do these type of things, and then. So let us. I have to just. I'm in my room, so I have to check out. So let's meet in another 20 minutes maybe, or so 30 minutes. Let's say हम break अभी कर लेते हैं.